In this game, entitled Cannon Assault and Survival, the player is challenged to perfect the controls which adjust for delta Y, initial velocity, and the angle of the shots to avoid being overrun by two types of enemies.
The motion of the cannon and the ball is dynamic and changes for the entire run of the program based on specific keystrokes made by the user. The cannon's vertical displacement can be adjusted using the W and S keys. Pressing the W key increases the height of the platform, whereas pressing the S key decreases the height of the platform. In a similar fashion, the angle of the ball can be adjusted using the left and right keys, the right key denoting clockwise movement and the left key denoting counterclockwise movement.
Despite its bland looks, the game can get addicting as players feel the need to beat the high score. But enough about the game. Let's delve deeper into the physics of how the game works. It is evident once the game begins that projectile motion is at play. The cannon shoots out cannonballs that fly according to projectile motion, path traveled by an object that is influenced only by the initial launch, speed, launch angle, and acceleration due to gravity.
The ball's initial velocity upon instantiation is represented in this line of code, where the angle and the strength of the vector is determined by the user. It is to be noted that the strength, or rather the magnitude of the initial velocity vector, is adjusted using the up and down keys. For our program, the maximum initial velocity that the ball can have is 13, which is the length of the vector, to be specific. The program is set to change the position of a ball according to its initial velocity vector. Specifically, the move method tracks the velocity vector at every tick, or each time frame, and moves the ball according to the angle and magnitude of the vector. The exact x or the precise x coordinate of the ball is determined by the length of the x component of the velocity vector. The same thing applies to the variable exact y, where its y coordinate is determined by the length of the y component of said vector. Altogether, the object's location is set to the endpoint of the velocity vector, which is determined by its x and y components. Evidently, the ball class is the main class that uses these sets of methods. At this point, we know that the ball's position changes according to its velocity vector. However, you may be wondering why the ball doesn't just fly off the screen. What exactly gives it the negative acceleration that allows the y-coordinate of the ball to progressively decrease in a way that simulates or models projectile motion? This line of code is what allows the ball to fall back down, following a parabolic path. Without it, the ball would float in the air like so.
To tie this back to the UAM equations, the equation used in this game would be equation number 1, where the new velocity equals the original velocity plus the acceleration times time. The original velocity was first stated here. The gravity variable would be the acceleration of the ball in the y direction. In this case, the ball's y position will change at a constant rate based on the fixed length of the gravity vector that alters its value. For each tick in the program, the gravity vector, which remains constant, is added to the velocity vector of the ball. The gravity vector has an x offset of 0.0 and a y offset of 0.25. Therefore, only the y coordinate of the ball is affected. Due to the change in velocity, the x and y coordinates are adjusted with the code mentioned earlier. We hope you have a stronger understanding of how projectile motion is integrated into this project after our explanation. Until next time, yum!